Okay, example 2, part 2. We had some data, temperature, emergency calls. We look at the scatter plot and go, that kind of looks like a line, doesn't it? But again, a mathematician doesn't just go, that looks like a line. Good enough for me, man. We do a test. We test to see if the correlation value, the R value that we got from that data that we just enjoyed, does that suggest a linear relationship? So again, example 2, let's do a hypothesis test of this. I want to remind you again that when you do a hypothesis test, it's called a hypothesis because it involves your population. In other words, we're testing the theoretical correlation rho, all right? And just like example number 1, we assume that these two variables do not have a linear relationship and therefore would have a rho value of 0. So just like the first one, let's assume they do not have a linear relationship and therefore their correlation for the whole population would be 0. That is called a hypothesis. We don't know how the entire population behaves, but we use the data from our sample, the R, to test it. Okay, so this again goes back to the steps that we've discussed for doing a hypothesis test, and there we go with that. All right, now the alternative. Here's the thing on this one, which is a little different from example number 1. So be careful when you read these. This says, is there a significant linear relationship? Did it specify positive linear or negative linear? No, it just said linear. So if you go back to this continuum that shows you the values that R could be, I want to remind you that the more you deviate from 0, the more linear you are. And since this question didn't specify what type of linear, positive or negative, it just said linear relationship. So, not equal 0. That allows for both possibilities. So this question didn't specify whether we were to test positive linear, negative linear. Now look, the scatter plot suggests positive, but the question just said test to see if it's linear. Not equal 0. There you go. All right, we've already identified our test statistic. That's always going to be the same, t, and that'll impact our rejection region here. So we'll draw our t-curve here. I didn't do a very good job of leaving space here. I'm going to move compute down a little bit there. Alrighty, so alpha is 5%, and so we'll take that 5%. Now, this is the importance of having this correct, not equal 0. So we're saying you could either be significantly higher or lower, and so that would be 0.025 in each of those tails, because that's half of 5%. In other words, because of the not equal, we have a two-tailed test going on here. And the other element is degrees of freedom, n minus 2. Let's see, how many data points do we have? 1, 2, 3, 4, 5, 6, 7. 7 sample data points. And so that's 5 degrees of freedom. That's important. So, here's how we would read this from our beautiful t-table now. We go to our good friend, the t-table, and here we go. You guys see this row here that says 2 tails? Aha, because it's a two-tailed test, not, and 5%, a 5% two-tailed test. I would like to point out to you that a 5% two-tailed test is the same column as a 2.5% one-tailed test, because 5% split between 2 tails is the same thing as 2.5% in each of the one tail. So either way you want to interpret that, it's the same column, 5% two tail, 2.5% one tail, and didn't we say 5 degrees of freedom? So that looks like 2.571. And because of the two-tailed nature of this, we'll have the positive as well as the negative. And there are two possible rejection regions. So, I gotta get rid of this degrees of freedom thing here. Board space, I'd love to have more board space if I mentioned that. All right, if the t-value ends up being less than the negative 2.571, and you know what that'll mean? That would mean that they're negatively linear, they have a negative linear relationship because it's on the negative side. Or it'll be greater than 2.571, which would indicate that they have a positive linear. Looking at the picture, if it's going to happen, it's going to be probably on the positive linear, don't you think? Okay, so there's that. E, compute. Now we go stick the numbers into that test statistic. We go sample some data. That was the table we had up here a long time ago. And find the R value of 0.811. N minus 2, we sampled 7 days, 7 data points, minus 2. 1 minus parentheses, 0.811 squared. And this is order of operations here. So, you know the speech. I have to hope, and look, many people before you have been able to crunch those numbers just fine. So I would hope that you're in the same boat there. And so, pushing buttons, 3.09967. Not sure why I kept so many digits. Because once you saw the 3, you knew it was out there. And it's positive. So, that 3.09967 is indeed in that upper tail. It is indeed greater than 2.571. We're going to reject that null hypothesis. And if we reject the null, which was the assumption they were not linear, that supports the proposition that they're linear. If you reject the null, that supports the alternative, and the alternative was they are indeed linearly related. So the appropriate interpretation would be now to give, would be to say, at the 5% level of significance, there is a significant linear relationship between these two variables. And there you go. So, you hopefully looked at that and said, yay! Because of that outcome, it does make sense to build the equation of a line to model that data. So there's more to be done. Let's go find the regression line in part 3, shall we? Yeah!